Okay, so today's video is going to be about quantum mechanics, and we will be talking about particles and forces. Okay, now before we get to the main quantum mechanics, in the forces topic, let's talk about the forces in macro level, like planet or human level. Now, we know that in macro level, gravity is the strongest force, right? Strongest force. Now, what I meant by strongest force mean there is no other force which is stronger than the gravity, the force of gravity, gravitational field strength. So, how? Okay, let's suppose if we have our sun, okay, and then we have our particle. So, in our particle, let's suppose our Earth, and this is a distance between Earth and Sun. Let's suppose R. So the formula for this force will be F equal G m1 and m2 r square. Here m1 and m2 are the forces of the two objects, and r square is the distance square between the objects. G is a constant, gravitational constant. Okay, now when we talk about um, in macro level, gravity is the strongest force. No force is stronger. No force is stronger than gravity. Okay, gravity surpasses all forces in macro level. And we have the example, the best example, black hole. Black hole. How strong its gravitational force is. Gravity. Even light can't escape it. Even light can't escape it. Okay, now let's go to the micro level, the main topic of our main topic. So now remember I told you that in macro level gravity is the strongest force, but guess what, in micro level that same force is the weakest force. Okay, here this force is recognized as one of the weakest force, and the sole example of this force is that particles behave in superposition state. Superposition happening. And since why is it weak is why it's weak. Sorry, wait. Why it's weak? I think you might know the answer already. Yes, the answer is in the equation. This equation, that the difference in mass, or the mass is so less, m is mean it's in nanometers, it's in nano level. So this force is literally negligible. It's negligible. Okay, And then, since it's negligible, quantum mechanics, since it's negligible, the properties of quantum mechanics behave different, are different. Okay, now what I'm trying to talk about is, we know about QED, right? Quantum electrodynamics, in which we have two particles, particle 1, electron, and let's suppose if it's moving in this direction, and what will happen is that at this point this electron will emit a photon, emit photon. When it will emit photon, it will recoil. It will recoil. It will recoil. So, and how we get the diagrams? The diagrams come from the Feynman diagram. Feynman diagram explain QEM, QED, like this. Okay, and these two, the downwards is matter and upwards is antimatter. And this is photon emit. Okay, so QED explains the electromagnetic force or the repulsion of like charges. I mean, because electron, it explains why electron coming closer to, in theory ways, it's the most accurate theory. It explains how they repulse. Okay, and what was it? They emit photon emit. Now uh, we will be talking about the same thing, but in a different way. We will be talking about QCD. The today's topic will be QCD, quantum chromodynamics. Sorry, dynamics. So we know that this is quantum electrodynamics and this is quantum chromodynamics. The word chromo is the main thing here. We know that we have particles, which is electron, and they orbit around a nucleus. This is a nucleus. Okay, and these are where this is where electrons roam around. Okay, now we know that there's some kind of electromagnetic force. Okay, electromagnetic force, and this electromagnetic force is inversely proportional to distance. Okay, This is me making it up. I don't want to write fully the word, so I'm just making it like this. So this force over here is inversely proportional distance. The further away the particle is, the more less the field of force of attraction. Okay, so they you could say that they, what if they get influenced by each other, but that cannot happen because there's a huge distance between them as well. Okay, actually I should use S, not D. S. Okay, so here the electromagnetic force over here is actually decreasing as we get away, we get separated from the center point, the nucleus. But when we talk about the nucleus itself and it having quarks, sorry, it has, what does nucleus have? Nucleus have protons and neutrons, right? Protons and protons and neutrons. So what actually happens is these protons consist of quarks, and the quarks are made of up, down, and so on. There are many quarks. Now when these quarks are combined, okay, what actually happens is, we know that particles, we know that particles we know that particles what do particles, what's the speed? Have huge speed. Okay, so yes, it's a good, there is a question that, if there could be a question that if they have such huge what do you call this, they have such huge speed, that means they would require the force which is going inwards must be very strong, right? Yes, that is what the gluon force is. Gluon force, or the strong force. So gluon is a particle force. What this force is, that on stretching the particle, this force gets stronger. Okay, it's actually getting stronger. There will be a point which will be reached, point will be reached. We're not saying it won't happen, it will happen, will be reached, in which the particle, the this it the stretch breaks. Okay, breaks. And on this bond breaking, or the stretch breaking, now we have two pairs of particles. Let's suppose this is mu, strange, this is mu, strange. These are called pions. Now this force over here, these lines, these over here, this symbol, these represent gluons. Okay, and in we are now going to talk about color. Yes, color. How the QCD represent forces. okay, which is with red, blue, and yellow. It was green, sorry. And these are charges of particles. In QED, what do we have? A positive and a negative. But here we have red charge, blue charge, and green charge. They are charges. Remember that. And each combination, each combination is different. Okay, meaning red plus blue plus green gives 0. They give their total is always 0. So that means red is minus G minus B. So actually a sum of these forces is actually the negative sum of the other two forces. For the first, let's suppose if you want to find one, the other one will be negative sum of the both other forces. And this could be taken as G is equals to minus R and minus B, and also different combinations are there, and each depends. And remember, if they're like, they will cancel each other. They like, they will cancel each other. So unlike, sorry, so it's green, it cannot. So you might have noticed that they are in the pair of 3. They can be in pair of 2 or 1. 2 or 1 were possible at the start of Big Bang. In the first some time, we had 1 or 2 quarks. Like there was no pairs. Okay, if it was 1 particle or 2 particle pair, or the of course 3 particle pair is the common one, the most one, mostly done. But we could create 2 or 3, 2 or 1 pair in the particle collider or hadron collider. Okay, so these over here actually have color. Actually, in color is actually carrying 2 kinds of charges. Okay, carries both carry 2 charges at the same time. It's actually superposition of the charges. Superposition. Superposition. Now, talking about, they are mostly similar because QED, QCD. Now, particles for QED are proton, for this gluon. Okay, particles. Then both particles are massless. Now both have fields. Now what's the difference here? Part QED is no charge, right? It's neutral. Because photons don't have charge, neutral. But here we have the change. We have a charge, which is the color which I was talking about. So that's the thing. Color is the difference between quantum chromodynamics and quantum electrodynamics. Color are the color forces, the forces which each color is this is not by the way, this is nothing regarding the each like the common colors, but totally separate. It's just like they gave the name color, which is red, blue, and green. So this is full red, this is full blue, this is full green, this is R, strange R, strange green, strange blue, and in the middle is black and white. Black, white. Now, this is how it is actually. Diagram version. Sorry. Diagram version. And they can be different combinations. We could have superposition of G, B plus. This is just an assumption. I'm not sure if it this actually is something which can be done, or it's opposite. Sorry, but they can be things like this. And look over here. This was nothing but a superposition state. Superposition factor. Okay. So recently, what actually happened was uh, in the space quantum communication, quantum mechanics, space quantum, I think communication or something like that. I'm not sure. They actually entangled two quantum particles. Okay. Oh yeah. By the way, quantum particles. I remember the forces in quantum mechanics have to be quantum forces, right? They have to be quantum forces. Remember that. We take them as quantum forces. We give them a good name. So the distance between them was 12 kilometers, and it was a huge distance. And this actually proved entanglement using entanglement is you can just take this extra knowledge. Entanglement proves it, hence proven, which Einstein called the famous spooky action at a distance. Spooky action at a distance. At a distance. Yeah. Thank you. Enough. That's it.